Hello everyone, today we are going to learn about the package QuantumOps. So this is basically about various types of operators that can be used in RStudio, that is both quantum mechanical as well as mathematical operators. First of all, here I am representing a vector as a ket. Ket returns a normalized vector. I will show. So I am applying this ket operator to this vector and I will get a result which is actually a value divided by this whole column vector. That value is actually the square root of the sum of the coefficients. Here you can see the ket of this vector is a normalized one, and the values can be shown here. This is actually obtained by dividing it by the square root of the sum of coefficients. And if you want to convert a binary digit to a decimal one, the command is convert_binary to decimal, and we can see that corresponds to 17 in decimal. If I am adding one more digit to that, I will get another corresponding decimal number. If I want to find the binary number of a particular decimal number, the command is convert_decimal to binary of 10. So I have this much amount of bits in my answer, so I don't want all these things. I can eliminate all these bits by commanding the rounding. So I am here including the command for with the previous code, which I will get this shrinked to 4 digits or 4 bits. This is in order to find adjoint of a particular vector. I can do this operator. This is actually found by dividing the whole vector by square root of 1 plus 1, that is 1 by root 2. So 1 by root 2 and 1 by root 2. And here a 4 component vector is shown here. And then Dirac operator applying on this, we will get coefficient 0.5, 0.5, 0.5, 0.5 for each of these values. And you can see that the square of the coefficient when added will gives to 1, that is 0.25, 0.25, 0.25 and 0.25. So the total probability of all these 4 states are equal to 1. If you want to find the distance between two vectors, so the command is dist ket1 and ket2. So the distance between this particular two vectors are 0.7653, and so the probability of ket 1 1 1 1 is actually 0.25, 0.25, 0.25 and 0.25. The same thing we did here. Here we got the coefficients as 0.5. The square of the coefficients will give you this probability. So it basically is the same thing, one in terms of the coefficient and another in terms of the probability. So these x, y, z are the Pauli spin matrices in quantum mechanics. It is one of the special 3 types of operators in quantum mechanics. You can multiply the Pauli spin matrices with particular ket, two-dimensional ket, and the results are shown here, and the Pauli spin matrices x, y, z are also shown here. The determinant of Pauli spin matrices is actually -1, and this is unitary matrix. Unitary matrix means that for a vector A, if its the transpose is same as the matrix, then it is called a unitary matrix. So A transpose A is equal to I. So this is to check whether a matrix is particular vector is unitary or not. Okay, this one here we added the tolerance level. So up to this much tolerance, it will check whether the particular matrix is unitary or not. Okay, so here this is about a cubic transformation. This n is the number of, or this 1 is the number of bits for the input, and this is for the output. We want to transfer this function over this input and output, and the matrix corresponding to that process will be given by this operator. And you can see, in order to transmit x minus floor of x by 2 times 2 from a 1 bit to a 1 bit operator, we want this matrix as the transformation matrix. So various other examples are shown here. if I am transmitting 0, I will get an identity matrix. So basically multiplying it with will give you the same result. And so various other examples are shown here. If you want a higher dimensional poly spin operator, the dimension should be included here, and submitting will give you 3 matrices of n by 9 by 9 order. This function is actually for multiplying operators. So if you want to multiply a poly spin matrices with a get operator, this u of poly spin matrix x and get is shown. You will get the result. If you want to multiply 2 Hermitian as well as a get, the command is this. If an identity, a poly spin matrices and a get, you can multiply all these things inside the u bracket. Similarly, you can do all these things. So if you want to plot the probability of a particular state, you have the command plot probability of the particular get, and you can add the corresponding colors for that. So for each of the particular values, the probability of occurrence or state, probability of that state is shown in this picture. You can change with the values, say 1, 1, 1. You will get equal probabilities, that is 0.25 for each of the states. This is another operator, T operator, and teleport get. These are some operators related to quantum mechanical and qubit transformation. So this is test gate of CX. Actually this is the input about that. So these are various types of gates, and how we can input different types of get in such gates, and how the result will be coming. Swap is another type of gate. So multiplying it with the get 0 1 0 0, and the swap matrix basically is this, and applying this on this get will give you this result. So, and this is actually rotational matrix with respect to z axis. So I am rotating my get with respect to z axis at an angle pi. So pi or theta is the angle at which I am rotating the particular get. I will get this as the result, and rotation matrix for theta as pi is actually this much, and you can do the same for y-axis and with respect to y-axis as well as z-axis, and the results are shown here. Rotation matrix are very important in quantum mechanical operations, especially for rotating specific wave functions and all. And repeat tensor is doing it in a diagonal way. So the poly spin matrices X are placed in the off diagonal or non-diagonal component. Okay, and same is done here also. The poly spin matrices Y is placed at the opposite diagonal. So this command basically generates a random undirected graph, which means that we get a graph or a network, and in which 1 is connected to 3, 2 is connected to 2, 2 is connected to 4, 3 is connected to 1, and we will get a result of such graph. And this is another controlled Z gate. It's a particular type of gate, and we are applying this get on this controlled Z gate. And so creates a quantum gate defined by 4 angles as demonstrated by Berenso 1995. This is what the G command actually means. It's a particular type of gate, and we are applying the get 1 0 onto that. We will get the result. So these are about various types of gates, operators and converters, and that can be seen in quantum operators ops. Thank you.